Welcome to the workshop. Today we want to take a look at section 2.6, applications. So we're first going to look at an application of mathematical induction. We're going to do a proof, but it's going to be for something that we actually took a look at back in chapter 1. So let's take a look at that example a moment. So again, back in chapter 1, section 3, a knapsack problem, we saw that a set with n elements has exactly 2 to the n subsets. And that's what we want to take a look at here, is we want to prove it. And we want to prove it for any integer n, any non-negative integer, so 0, 1, 2, and so forth. So for our proof, okay, we've got we need to have our statement, and this one looks a little bit different because it's not actually an algebraic expression for us to evaluate. Well, it is, but it's 2 to the n, and that's the only thing. It's not quite equals another algebraic expression. So S of n, our statement that we want to prove, is a set with n elements has 2 to the n subsets. And this is for as small as 0. Now this is going to be a lot of writing, right? I'm not doing algebraic manipulations, so I'm going to express what's going on. I'm going to talk about it for the most part. The one case that's not true for, or the one situation that we're not going to simply be writing out what exactly is going on, is the base case. I mean, it's still pretty much true, but there is a computation, and we look, hey, this stuff. Excellent. So base case. We want to let n be equal to 0. Then the set that we're talking about, there's only one set with 0 elements in it, and it's the empty set. Then let's see here, the set is the empty set, which has exactly one subset itself. The only subset of the empty set is the empty set itself. So, which is in fact 2 to the 0, which is 1 subset. Thus, S of 0 is true, because a set with 0 elements has 2 to the 0 subsets. Excellent. So the next thing we want to look at is the inductive step. All right, let's assume that S of k is true. Then a set with k elements has exactly 2 to the k subsets. Excellent. Okay, so we're assuming that a set with k elements has exactly 2 to the k subsets. And what we want to do is we want to show that a set with k plus 1 elements has exactly 2 to the k plus 1 subsets. And it's actually pretty straightforward and easy. It relies on one observation that I think is pretty obvious. We'll see what you guys think. So let's let n be equal to k plus 1. Furthermore, we're going to let A be a set with elements A1, A2, A3, all the way up to, let's see, that's supposed to be a 3, 3 all the way up to a sub k and a sub k plus 1. So let A be the set with k plus 1, or a set, right? Let A be this, a set with k plus 1 elements. I should phrase it that way. That'd be good. A set with k plus 1 elements. Okay, easy enough, straightforward. Then the set, so if I consider the set just A1, A2, A3, all the way up to A sub k and end there, right? So if I take all of the elements except for this last one, then I have k elements. Then the set is a set with k elements. And 2 to the k subsets. So this set is a set with k elements and 2 to the k subsets. Since there's k elements in it, there's 2 to the k subsets of it. All of these subsets, are subsets of A, right? This itself, this thing is a subset of A, so all of the subsets of this are in fact subsets of A. But in particular, they're all of the subsets that don't contain this element. So all that we have to do is add in all of the subsets that do contain that element. Because one of the two things is true. Either the subset contains a sub k plus 1, or the subset doesn't. So everything fits into one of those two categories. And so far, we have everything that doesn't contain the element a sub k plus 1. So how do we find all of the subsets that do contain a sub k plus 1? Well, all we have to do is take all of the individual subsets of this and add a sub k plus 1 to all of those subsets. So by adding, let's see here. So all of these are subsets of A, which do not contain a sub k plus 1. By adding, or by adding, that's fine language. By adding a sub k plus 1 to each of these subsets, we find all remaining subsets of A. So again, either a subset contains a sub k plus 1, or it does not contain a sub k plus 1. Fits into one of these two categories. So we have all of the ones that don't contain a sub k plus 1. Now everything else must contain a sub k plus 1. So all we have to do to find those is add a sub k plus 1 to all the ones over here. So thus, there are, right, we found 2 to the k subsets of this guy, plus 2 to the k subsets where, right, we took those same 2 to the k subsets and joined a sub k plus 1 to them. When we did that, that gave us 2 to the k new subsets. So thus, there are 2 to the k plus 2 to the k, which is 2 times 2 to the k, or 2 to the k plus 1 subsets of A. Fantastic. That's it. Thus, S of k plus 1 is true. Therefore, by the principle of mathematical induction, S of n is true for all non-negative integers. Excellent. Indicate the end of our proof, and we're all set. That's it. So this is a proof by induction that every set with n elements has 2 to the n subsets. An idea that we presented and actually demonstrated already in section 1.3. All right, so that's an application of induction, right? Proofs by induction, mathematical induction. We'll continue on with some other ideas in this section that improve our counting techniques or introduce some new counting techniques. So I'll see you guys back here in the workshop in just a little bit to take a look at some counting methods.